Dear students, I welcome you for the today's lecture. Today we are going to understand the concept of conductivity, conduction, thermal conductivity, and the thermal diffusivity. And then we will discuss related to the numericals. So conduction, the transfer of energy from the more energetic particles of a substance to the adjacent less energetic ones as a result of interaction between the particles. The energy, difference of the energy, that is the kinetic energy, when we will say the kinetic energy associated with the molecules, that defines your temperature. So this higher energy particles, that means the higher temperature of the material or the substance, in comparison with the less energetic or the less temperature material, there is a change, there is a difference, and this difference leads to the process of conduction. In gases and liquids, conduction is due to the collisions and diffusion of the molecules during their random motion. And liquids, solids, they are having the highest vibrations, higher free electrons, and as a result, in the process of solid, the conduction is to a higher extent, and as a result, they are said to be the good conductors of heat, good conductors of heat. So the solids, they are the good conductors of the heat, and due to the continuous vibrations of the molecules, and as a result the energy transport by the free electrons, that leads to the process of conduction. However, in case of gases and liquids, this availability of the free electrons in comparison is less. So the molecules, they are freely arranged. So these molecules itself physically move from one place to another. In liquids and gases, the conduction is due to the collisions and the diffusion. Collision से भी होता है gases and liquids में. The rate of heat conduction through a plane layer is proportional to the temperature difference across the layers and the heat transfer area. Now coming to the equation, the rate of heat conduction. When we talk the rate of heat conduction, that is related to the amount of the heat transfer per unit time. Amount of the heat transfer per unit time. So joules is the unit per unit time. Amount of the heat transfer, that is the joules, and per unit time, joules per second, that is nothing but the watts, that will be there. So joules per unit time, that is nothing but the watts. So the rate of heat conduction is directly proportional to the area through which the heat transfer takes place. Now in this case we have to consider this area A. That means the area for which the temperature is exposed, and this temperature, this area through which the heat is transferred, that area has to be taken into account. So area and the temperature difference, temperature gradient, that will be there, and is inversely proportional to the thickness delta x. or the length L through which the heat is getting transferred. जितनी ज़्यादा thickness है उतना कम rate of heat conduction रहेगा. That is, it is inversely proportional. So these metals are good conductors of heat. The outer electrons of the metal atoms are not attached to any particular atom. So they are free to move between the atoms, and when the metal is heated, the free electrons gains the kinetic energy. This means that the free electrons move faster and the transfer of energy through the metal takes place. This makes the heat transfer in metals very effective. However, your insulators do not have the free electrons, and so they do not conduct the heat like that of the metals. So in the other words, the flow of heat in a substance due to the exchange of energy between the molecules have more energy, and the molecules having the low energy. High energy to the low energy molecules are there. That is the transfer of heat from one particle of matter to the another by the direct particle to particle contact. So the direct particle to particle contact is there, but no physical movement of the particles that is associated with the process of conduction. So conduction occurs primarily in the solid because the particles are tightly packed together. The particles themselves do not change their position. This is very much important. Particles do not change their position. They only vibrate. Particles. That is, the molecules are in constant motion, so their speed is proportional to the temperature of the object. That is your kinetic energy of the molecules. When two objects come in contact, their surface molecules will transfer the momentum. An aluminum pot will conduct the heat from a glass stove top. Now, the equation Q, which is equal to is, or you can say the rate of heat conduction is proportional to the area, temperature gradient, and the length through which or the distance through which it is passed. So the constant of proportionality, that is given as the K. So K is the constant of proportionality, and which is defined as the thermal conductivity. And it is a measure of the ability of material to conduct the heat. What the K is? The ability of the material to conduct the heat. That is what the thermal conductivity is. Now this temperature dt upon dx, this is the temperature gradient. That means as I am increasing the distance, my temperature that decreases. The slope of temperature curve on a Tx diagram. Now you can look at this figure, first figure, that is the C. 30 degrees Celsius is the temperature on one end, and on another end it is 20 degrees Celsius. So there is a temperature gradient, and as a result the heat is getting transferred from higher temperature to the lower temperature. The distance through which the heat is passed is the 1 meter. Now in this case, one is your copper metal and another is your silicon. This K, the thermal conductivity of copper, is 401 watt per meter degrees Celsius, and the silicon is having the thermal conductivity of 148 watt per meter degrees Celsius. There is a lot of difference, 400 and 150 approximately. So how much amount of the heat that will be transferred, that is also going to vary depending on the material. Now this is the rest of the things are same, that is 30 degrees Celsius temperature. Here also the 30 degrees Celsius temperature on one side, and on the another side the temperature is 20 degrees Celsius. Here also on the another side the temperature is 20 degrees Celsius. Now, so the temperature gradient dt upon dx, that will be the same, that is of 10 degrees Celsius. Dx is 1 meter in both the cases. Area, that is also same. It's the rate of heat conduction is is equal to or depending only on the thermal conductivity. So it will be the ratio of thermal conductivity that will be there. So K, which is equal to 401, and K, which is equal to 148. Now if you will, one can calculate by considering the area per unit area and per meter length. So it is the per unit area we have calculated it, watt per meter square. Per unit area, when we calculate, that is the flux. Somebody was asking related to the flux. That is what we are talking, or we are interpreting the numericals in this respect. That is, we are talking in terms of a per meter square or per meter length, and for that simplicity we are using the heat flux, the terminology of the heat flux. So we can compare it very easily and conveniently whenever we talk in comparison with the per meter or per meter square. That is, when we talk per meter square, it is termed as the flux, heat transfer rate per meter square. That is nothing but the heat rate flux. And even sometimes it is convenient to talk in terms of the per meter or per unit length. So that is what we can easily compare all these terms, and as a result we use the different terminologies to compare it very conveniently. So this is the watt per meter square, this is the flux 4010, and the in case of silicon the flux is 1480. So the everything is same except the difference of the thermal conductivity. So if the thermal conductivities are higher, then we will obviously get the higher heat flux or higher heat transfer rates. So rates are higher when the thermal conductivities are higher. Then the heat is conducted in the direction of decreasing temperature, that is from higher temperature to the lower temperature, that is the heat is going to transfer, and the temperature gradient becomes negative when temperature decreases with the increasing x. What is that? The temperature gradient becomes negative with the temperature decreases with the increasing distance. So initially 8 मीटर के लिए temperature gradient is 10 degrees Celsius, and I say if it's a 0.5 meters, if it is a 0.5 meters, then temperature difference will be somewhat 7 or 5, whatever it will be. सेंटर में कितना आएगा रेजिस्टेंस के हिसाब से वो कैलकुलेशंस होंगे. We can calculate the temperature at different point depending on the distance also. इस distance पे कितना temperature रहेगा, इस distance पे कितना temperature रहेगा, that everything we can calculate, and that is what we study in our heat transfer processes. For that only we have to do the numerical analysis and interpretation of our basic equations. So the temperature gradients become negative when temperature decreases with the increasing distance, and this negative sign that indicates that the heat transfer is in a positive direction only. Heat transfer is in the positive direction. That means from higher temperature to the lower temperature, heat is getting transferred. Or you can also say that the negative sign indicates that the heat flows from inside surface to the outside surface. From inside surface to the outside surface, the heat that can flow. So this is the now in heat conduction analysis, A represents the area normal to the direction of the heat transfer. Now what is A? There is when you consider a three-dimensional slab like this, then the heat transfer, in which direction the heat is transferred. So higher temperature exposed area and lower temperature exposed area, that should be understood. The higher temperature exposed area and the lower temperature exposed area. So higher temperature का जो exposure है उस एरिया से लोअर टेम्परेचर का एक्सपोज्ड एरिया में हीट ट्रांसफर हो रही है, and that is what the heat area A represents the area normal to the direction of the heat transfer. And this law, that is the Q, which is equal to minus Ka dt upon dx, this is called the Fourier's law of heat conduction. And this Fourier, that is nothing but the French mathematician and physician. He has worked for infinite series of trigonometric functions. Trigonometric functions is maybe a Fourier function, we know it. And he established the partial differential equation governing the heat diffusion. So this is the governing equation for the heat transfer associated with the heat of conduction, heat due to the conduction. Now the thermal conductivity. Thermal conductivity, that is the measure of the ability of a material to conduct the heat. It is the measure of ability to conduct the heat. The rate of heat transfer through a unit thickness of a material per unit area per unit temperature. The rate of heat transfer, that is what the thermal conductivity is, the rate of heat transfer per unit thickness of the material per unit area. This is the K thermal conductivity that is there, and it is having the units of watt per meter degree Celsius. So the heat transfer rate per unit thickness of the material per unit temperature difference. So this thermal conductivity of a material is a measure of the ability of material to conduct the heat. The high value of thermal conductivity indicates that the material is a good heat conductor, and the low value indicates that the material is a poor heat conductor, or it is also called as the insulators. Now, if you will look at the different figures of thermal conductivity, the diamond, it is having the thermal conductivity of 2300 watt per meter degree Celsius, but it is very costly, so people doesn't use it. Then silver, that is 429, and copper, that is 401. However, the cost of silver and copper, that is drastically different. Nowadays, the cost of the silver, that is around 60,000 rupees per kg, and cost of the copper, say around 1,000 rupees per kg. So drastic difference in the cost, but a minor difference in thermal conductivity that is there. Then aluminum, which is also the chip material, that is having the 237 as the thermal conductivity. Then poor conductors, that is the glass fiber, it is having the 0.04 as the thermal conductivity, and the air, which is 0.026 watt per meter degree Celsius. So this is the air which is considered to be as a good insulator, and even better than that is the vacuum. So if you are reducing the pressure, uh, as a result you are in decreasing the thermal conductivity. And urethane foams, which is available in your fridge or so, as the insulating material, which is having the thermal conductivity of 0.026. So here also the lower thermal conductivity, it's a graph indicating that the thermal conductivity K for various materials. The gases, which is your hydrogen, helium, air, carbon dioxide, is having the lower thermal conductivities, that is 0.01, that is air is 0.26. Then the insulators here, the foam, which is also same as 0.26, 0.026, which is the foam also. Then the wood, fibers, then oil, water, mercury, rubber, food, rock, oxides. These are all your non-metals. Then your metal alloys, pure metals, and non-metallic crystals having the higher thermal conductivity. So the thermal conductivity of gases such as the air vary by a factor of 10 to the power 4 from those of the pure metals such as the copper. So 400 and 0.026 is that of the air, and 400 is that of the copper. So that is the difference of 10 to the power 4. The pure crystals and metals have the highest thermal conductivities, and the gases and the insulating materials have the lowest thermal conductivities, and that is why we use them as the insulators. The thermal conductivity of an alloy is usually much lower than the thermal conductivity of either metals of which it is composed. So it's alloys. Alloys, they are having the lower thermal conductivity. Again, this is related to thermal conductivity. Now coming to the thermal diffusivity. Thermal diffusivity, that is the it is defined as the heat conduction per storage. That is thermal diffusivity. It is the ratio of thermal conductivity to the thermal capacity. Thermal conductivity to the thermal capacity, capacity to store that heat, capacity to store that heat. And that is why in general we call the Q, which is equal to mCp delta T. So mCp is nothing but the amount of heat that can be stored. So Cp is what? The specific heat of a material. Specific heat, that is the heat capacity per unit mass. Cp is the specific heat, and which is representing the heat capacity to hold. So that is the thermal capacity or the heat capacity. Rho से multiply कर दिया, that becomes your rho Cp. That is the heat capacity per unit volume. So that is the per unit volume. Rho Cp is the heat capacity per unit volume, and the heat capacity per unit mass, that is simply the Cp, specific heat, and having the units of joule per kg degree Celsius. So the thermal diffusivity is the ratio of thermal conductivity to the thermal capacity or the heat storage. So heat conductivity, that is the thermal conductivity, that is which is K, and the heat storage is nothing but your thermal capacity, which is rho Cp, rho multiplied by the Cp. So K upon rho Cp, which is equal to the alpha, that is nothing but the thermal diffusivity. So thermal diffusivity alpha, which is nothing but the heat conduction upon the heat storage, or the thermal conductivity upon the thermal capacity, which is nothing but K upon rho Cp. K upon rho Cp is the thermal diffusivity, and it is having the units of meter square per second. Now, when K that is there, thermal conductivity, it's the ability of a material to conduct the heat, and rho Cp is the amount of the heat that can be stored, and rho alpha is your thermal diffusivity. It is the speed of propagation of heat into the solid when temperature varies with the time. So it will indicate the speed of propagation of the heat. So thermal diffusivity is nothing but the speed of propagation of the heat into the solid when temperature varies with the time. It's a speed. That is why it is having the unit of meter square per second. That is the meters per second is your velocity. So speed of propagation of heat into the solid when the temperature varies with the time. So it's the material that has the higher thermal conductivity, or so whenever the value of K that is high, rho Cp same hai, and K is higher, that means the thermal diffusivity will be more. So a material that is having the higher thermal conductivity will have the higher thermal diffusivity. However, the rho Cp, which is nothing but the heat capacity per unit volume, which is inversely proportional. So as this heat capacity per unit volume increases, the thermal diffusivity decreases, क्योंकि उतनी अमाउंट ऑफ द हीट स्टोर हो जाएगी. ज्यादा हीट जब स्टोर करने की कैपेसिटी है उस मटेरियल की, तो वो आगे कैसे ट्रांसफर करेगी, irrespective of the thermal conductivity. Higher thermal conductivity है, but still I can store the more amount of the heat. तो पहले तो मैं अपना हीट स्टोरेज का कैपेसिटी फुल करूंगा, उसके बाद में ही मैं कंडक्ट करूंगा. So that is what the is inversely proportional. So the larger the thermal diffusivity, the faster the propagation of heat into the medium. That is what the speed of propagation of heat into the solid when temperature varies with the time. That is what the larger the thermal diffusivity, the faster the propagation of heat into the medium. So smaller values of thermal diffusivity means that the heat is mostly absorbed by the material. Absorbed by the material, that means rho Cp ज्यादा है उसकी, तो ही एब्जॉर्प्शन ज्यादा रहेगा. जितनी हीट आ रही है उसमें से ज्यादा मैं एब्जॉर्ब कर रहा हूं, तो आई कैनॉट डिफ्यूज इट, आई कैनॉट progress, allow it to proceed in the forward direction. That is what the speed of propagation of heat into the solids. So this is what the thermal diffusivity is. So speed of propagation of the heat into the solids. किस रेट से हीट प्रोपोगेट होती है? हीट प्रोपोगेट होती है थर्मल कंडक्टिविटी से, बट किस रेट से हीट प्रोपोगेट होती है? दैट इज द into the solid, that is the thermal diffusivity. So it's a meter square per second units, and thermal diffusivity of the solid silver, that is 149 into 10 to the power minus 6 meter square per second. For copper it is 113 into 10 to the power minus 6. For wood it is 0.13 into 10 to the power minus 6. That is what the different materials they vary. Generally, when we talk related to the heat transfer, we talk related to the copper, aluminum, iron, then your ice, then bricks, different types of the bricks, then the glass and glass wool, water, and the wood, and then the air and other materials only we generally talk in terms of the heat transfer. So this is the thermal conductivity of the various materials. In different books, you can get the slight change in the values also. Now this is what the Fourier law is saying. The heat rate, that is what Q, which is equal to minus Ka dt upon dx. dt upon dx is nothing but the temperature gradient in the direction of propagation, and that is why it is negative. All the heat is moving from inside to the outside. K is the thermal conductivity. Dt upon dx, which is equal to change in temperature, that is what? The T2 minus T1 upon the delta x. So Q double dash, which is nothing but the heat flux. The representation of Q may be different, but the basic formula, which is equal to Ka dt upon dx, with the units one has to remember. जो यूनिट्स में गड़बड़ होगी तो गड़बड़ ही गड़बड़ है. So Q, which is equal to Ka dt upon dx, when you talk in terms of the flux, that is Q upon A, which is become equal to minus K dt upon dx, and having the units of watt per meter square. Now coming to the second mode of the heat transfer. This is the first mode of the heat transfer, that is the conduction. Now second mode is the convection. Convection, that is generally associated with the liquids and the gases. The Newton's law of cooling here required. In case of convection, we are studying the Newton's law of cooling. In case of conduction, we have studied the Fourier's law. Fourier's law of conduction, which is incorporating the K thermal conductivity. Now in case of convection, it's the Newton's law of cooling, and which is represented by equation Q, which is equal to HA into delta T, where H is the convective heat transfer coefficient. That is what? It's a convective heat transfer coefficient H, and it is associated with the convection. Whatever associated with the conduction, it's a conductive heat transfer, K, thermal conductivity we call it. So here also the Q is directly proportional to the temperature area into the temperature gradient, and this H is the convective heat transfer coefficient, and this is having the units of watt per meter square Kelvin. So one has to remember this formula of and the details of which we will study when we will study the convection in details. So Q, which is equal to HA into delta T. Then the next is the related to the radiation, that is the Stefan-Boltzmann law, which is represented by the thermal radiation, which is the sigma Stefan-Boltzmann constant, epsilon and to the temperature raised to the power 4 for the surface, to the temperature raised to the power 4 for the surrounding. So this is what the radiation in terms of the photons that will be there. That is the electromagnetic waves that will be transmitted. The energy transmission is with the help of the photons. In case of a convection, the energy is transferred is because the fluid particles actually move. There is physical movement that takes place. When you heat liquid into the beaker, say, So bottommost surface of the liquid that is heated, the material or the liquid which is in direct contact with the metal or direct contact with the glass, that will be first heated. That will be increasing its temperature, increasing its kinetic energy. When the kinetic energy of the molecules increases, these high kinetic energy molecules, they move from one place to the another place. That is what, as they are with the higher kinetic energy, एनर्जी ज्यादा है तो वहां पे मूवमेंट ज्यादा आएगी ही आएगी. And that is what the major difference for the human beings also. When, if you will think, we generally say that बहुत energy है इसकी, so those people, they work to a higher extent also. And that is what the difference of the energies, that is also applicable for the human beings also, not only to the physical to these bodies, but it is also applicable for the human beings. तो एनर्जी तो कुछ लोगों में ज्यादा होती है, बट वो एनर्जी किस पर्पस से यूटिलाइज होती है? वो एनर्जी पॉजिटिव थिंकिंग में यूज हो रही है, या फिजिकल मूवमेंट्स में यूज हो रही है, या ब्रेन मूवमेंट्स में और ब्रेन थिंकिंग में यूज हो रही है, या फिर अनप्रोडक्टिव एक्स्ट्रा एक्टिविटीज करने में यूज हो रही है? दैट इज व्हाट वी आर यूजिंग द एनर्जी इन डिफरेंट वेज. तो क्रिएटिव फॉर्म में जब एनर्जी यूज होगी, तो दैट विल मेक यू द मोर कन्वीनियंट एंड मोर इफेक्टिव. So this is for the human being. This is what we have already seen. Now coming to the numericals of this heat conduction. So let us first study this numerical. An asbestos board having the thermal conductivity K of 0.1 watt per meter Kelvin is subjected to a temperature difference dT of 10 degrees Celsius across its faces. So asbestos board है, उसकी thermal conductivity दी है and temperature difference भी दिया हुआ है 10 degrees Celsius dt. Area of cross section दिया हुआ है through which the heat is getting transferred is 5 meters square, and the thickness is given as 0.05 meter. That means 5 centimeter thickness. So calculate the heat transfer rate and the heat flux across the board. Our heat transfer rate equation, which is equal to Q, which is equal to Ka, temperature gradient upon the distance, dt upon dx, or the distance, dx is nothing but your distance. So K is given as 0.1, area of cross section is 5 meters square, into the temperature gradient or temperature difference is 10 degrees Celsius, and the thickness through which the heat is transferred, that is 0.05. So it comes as the 100 watts. And if you calculate in terms of the heat flux, then the 100 watts upon the area A, that will be equals to 100 upon 5. This is nothing but 20 watts per meter square. So this is the first numerical. Then let us think of a second numerical where we are going to calculate the thermal conductivity. In this case, only these terms, that is Q, K, A, dt and L, means 1, 2, 3, 4 and 5 terms you need. So these 5 terms, उसमें से कुछ terms निकालने की है, कुछ terms दी है. Again here also Q, which is equal to K dt delta T upon delta X. So an iron plate of area A, 2 meters square, conducts the heat Q at a rate of 100 kilowatt. 100 kilowatt hai, so convert it into the watts. When the temperature difference across the plate and plate, which is 0.05 meter thick, 0.05 it is maintained at 70 degrees Celsius. What is the thermal conductivity of the iron plate? Now in this case, the thermal conductivity that is not given. However, the heat transfer rate that is mentioned. So heat transfer rate, that is Q, which is equal to 100 kilowatt, and that is why we have multiplied it by with 1000 to make it the watts. and then K is the thermal conductivity which is to be calculated. A that is mentioned as the area, that is the 2 meter square cross-sectional area through which the heat is transferred, and the temperature difference of 70 degrees Celsius, and the heat is passing through a distance of 0.05 meters. So thermal conductivity of the iron plate, that comes as 35.71 watt per meter degrees Celsius. So this is what we can calculate. The first numerical, we have calculated the heat transfer rate and the heat flux. Here we have calculated the thermal conductivity, and similarly we can also calculate the area when other terms are known. We can calculate the temperature difference, other terms are known, and also we can calculate the thickness if the other terms are known. So 5 terms we are having, Q which is equal to K dt upon dx. 5 terms are there. Out of that we can manipulate with the other two. Now in this numerical, it is the relative terms which we will see. When the excessive heat is produced within the body, it must be transferred to the skin and dispersed if the temperature at the body interior is to be maintained at a normal value of 37 degrees Celsius. Human body normal temperature 37 degrees Celsius. One possible mechanism of the transfer is conduction through the body fat. Suppose that the heat travels through 0.03 meters of the fat is in reaching the skin, which has the total surface area of 1.7 meters square and a temperature of 34 degrees Celsius. Surrounding temperature, that is 34 degrees Celsius, body temperature, that is 57 degrees Celsius. Area mentioned is 1.7 meters square, and the thickness, that is the 0.03 meters. Find the amount of the heat that reaches the skin in half an hour. So Q which is equal to Ka delta T upon delta X. Now this Q is having the units of joules when we are multiplying it with the time. In the previous case, the units of this capital Q is the watts. So don't look at this Q. अलग अलग book में अलग अलग Q दिया है. Look at the formula. Time है formula में. That means the unit amount of the heat, joules. So in this numerical, it is the Q, which is the Q in terms of the joules, amount of the heat, amount of the heat per unit time. That is what the watts. Joules per unit second is the watts. So this is K delta T into T upon the L. K that is given as 20.2. This is also mentioned in the numerical, or it is collected from the data, which is the 20 joules per second meter degree Celsius. Then area